In this video, we're looking at section 5.3. It's called Gram-Schmidt orthogonalization. And before we jump into this section, I want to flash back to section 5.1, and we're going to look at the importance of having an orthogonal basis. So why do we care about an orthogonal basis? Well, imagine that we're in R2, and imagine that we've got orthogonal basis vectors. So we got these two basis vectors here. Let's call them B1 and B2. And they are perpendicular to one another. So the beauty of this setup is that if we then take any vector, let's say vector W, any vector W in R2, if we just project that vector W onto each of our basis vectors, so projecting onto B1 would give us that, projecting onto B2 would give us that, gives us an easy way of writing W as a linear combination of the basis vectors. So if we look at this projection onto B1 that we've got over on the left here, remember that we can shift vectors around. So we can visualize that vector as sitting over here. In other words, we've decomposed W into something parallel to B1 and something parallel to B2. So we can then write W equals C1 B1 plus C2 B2. The real advantage of working with an orthogonal basis is that it's easy to then describe any vector W as a linear combination of our basis vectors. So let's do a quick preview of the type of question that we're going to be answering in this section. So let's imagine now that we're in R3 and that we've got some plane, some plane that's passing through the origin, but that is tilted in space. So it's not the XY plane, it's something that's tilted in a more interesting way. And what we're going to want to do is find an orthogonal basis for that plane. So that means that we need to find a couple of vectors that are actually on that plane and that are orthogonal to one another. So in our picture, it could be something like this vector here, that vector there, orthogonal to one another, but also both lie on the plane, so that when we take the span of those two vectors, we are actually describing this specific plane in the question. So that's what we're trying to accomplish here. And let's jump into a first example. We're going to say let W be the span of, we're going to take three different vectors in R4. And what we want to do is find an orthogonal basis for W. Okay, so let's think about this intuitively for a second. W is a three-dimensional subspace of R4. So roughly speaking, you could say W is like a copy of three-dimensional space that is sitting in four-dimensional space. And W is tilted in that four-dimensional space in the same way that the plane was tilted in R3 in our previous discussion. So W is somehow tilted in R4. And what we want is to come up with three basis vectors that actually lie in that tilted subspace W. So we want those basis vectors to lie on W. We also want them to be orthogonal to one another. All right, so this is how we go about the process. We're just going to take the first vector that we see listed in the span. We're going to call that V1. So V1 is the vector 1, 1, 1, 1. Now, at each stage, what we're doing in this problem is we are building a partial basis for W, or for short, I might just say a partial basis. And we're going to call that partial basis X, just to give it a quick name. So at this point, after the first step, we have just that first vector in our partial basis. And we're going to go through two more steps. On the second step, we'll add a second basis vector, and then by the third step we'll be done. We'll have our entire basis. So X, just a short name for our basis so far. And really all we've done in that first step is just taken the first vector in W in that span and just put that into X. Okay, so now things are going to get more interesting in the next step. We're going to say V2 is, well, we're going to take the second vector in the span, 1, 2, 4, 5, and subtract off the projection onto X of that second vector, that 1, 2, 4, 5. All right, so let's see if we can draw a picture geometrically of what we're doing here. So we've got this second vector, 1, 2, 4, 5. Let's say it looks like that. We're in 4D, but nonetheless, we can draw a representative picture. And we're talking about projecting that vector onto X. Well, what is X? Effectively, at this point, it's just the vector 1, 1, 1, 1. So let's draw that going in some other direction. Okay, and let's see what we're doing when we take 1, 2, 4, 5 and subtract off the projection onto X. So projection of 1, 2, 4, 5 onto 1, 1, 1, 1 would look like that. And if we take 1, 2, 4, 5 minus this projection that we've just calculated, that would give us this vector here. So that's what we're calling V2. And notice that V2 is giving us something that is orthogonal to the vector 1, 1, 1, 1 that we were using in our first step. So taking the second vector and subtracting off the projection onto the first vector is exactly the right thing to do to come up with a second vector that's going to be orthogonal to the first one. Okay, so let's go through the details here. So we go 1, 2, 4, 5. If you want, you can be specific and say minus the projection onto 1, 1, 1, 1 of 1, 2, 4, 5, and we'll just practice our projections here. So 1, 2, 4, 5 minus, now we need the dot product of these two vectors, so that's going to be 12. And everything else is about the vector that we're projecting onto. So length squared of 1, 1, 1, 1 is 4, and we're going in the direction 1, 1, 1, 1. Okay, and then we can simplify our coefficient. 12 over 4 is just 3. So we're going to do things like 1 minus 3 is negative 2, 2 minus 3, negative 1, and so on. So we're building this vector now, negative 2, negative 1, 1, 2. So after this step is done, we've now got what I would call a partial basis. We're still going to continue to call it X. So think of it like after each step, we're improving our information about X. So we've got 1, 1, 1, 1, and we've got minus 2, minus 1, 1, 2. So to check that you are on the right track, these vectors here should be orthogonal to one another. That's the whole point of what we're doing. So if you check their dot product at 0, that reassures us that we are on the right track with this calculation. So we're going to do one more step here to find our third basis vector. All right, so for V3, we are going to take the third vector from the span. Let's look back for a second. Third vector in the span from the original problem was 1, minus 3, minus 4, minus 2. So we're taking that vector and we're subtracting off the projection onto X of that vector. Now, because X actually has two vectors in it at this point, there are going to be two different projections that we're subtracting off. So often what I'll do is I will just write down specifically what the projections are. So we're going to go minus the projection onto 1, 1, 1, 1 of our vector 1, minus 3, minus 4, minus 2. And then we also need to subtract off the projection onto negative 2, minus 1, 1, 2. The vector that we're projecting is still our third vector from the span. So the 1, minus 3, minus 4, minus 2. Okay, so basically what this is doing geometrically is we're starting with this vector, this guy here. We're taking off any part of it that goes parallel to 1, 1, and then we're taking off any part of it that goes parallel to minus 2, minus 1, 1, 2. And what that's going to leave us with is something that is perpendicular to both of those previous two basis vectors. Okay, so let's try it, and we'll convince ourselves that this works. So 1, minus 3, minus 4, minus 2, minus, okay, now we're going to do the projection onto 1, 1, 1, 1. So if we do our dot product, that's going to give us negative 8 divided by length squared of what we're projecting onto and times what we're projecting onto. And then minus, now we're working with our second basis vector. Dot product comes out to negative 7 divided by the length squared of this vector, -2, -1, 1, 2. So that's 10, and that's in the direction of what we're projecting onto. Okay, now in problems like this, we are free to clear the fractions by scaling. Because anytime we're talking about a basis, anywhere throughout the course, when we talk about a basis, we're just talking about our set of direction vectors for an object. You're free to scale those basis vectors. So in a problem like this, we would not want to spend a lot of time dealing with the fractions. We could just say, oh, we can multiply v3 by any number that's convenient to clear those fractions. So if we look at this minus 8/4 or -8/4 here, that's a nice integer. That's actually going to be a minus -2. So we could just call that +2, that's fine. But multiplying through by 10 would be really convenient. So 10 is actually the least common multiple of the denominators here. So let's talk about 10v3 instead. That would mean going 10 times our first vector. We're going plus 20 times 1, 1, 1, 1. And then our last coefficient here is plus 7/10. So as we multiply by 10, it's plus 7 times that vector there. Okay, and then we can get a nice answer for our third vector. So what this comes out to then, if we go through all the algebra, 16, -17, -13, and 14. So the question was find an orthogonal basis for W, and here it is coming up. So our orthogonal basis is, just looking back to our last step, we had 1, 1, 1, 1, and -2, -1, 1, 2. We've now added our third and final basis vector, which is 16, -17, -13, +14. So if you wanted to check your answer, you're just now confirming that all three pairs of vectors here, they have dot product 0. So you can check that and just convince yourself that you've done that properly. So these three vectors do actually describe that particular subspace W. They are on that subspace W, and they are orthogonal. So minor modification of this, sometimes we'll ask for an orthonormal basis. So remember, when we say normal, that's just referring to normalized vectors, so meaning we want to turn them into unit vectors. So if we want an orthonormal basis, let's normalize at the end of the problem. There's no reason to introduce messy fractions in the intermediate steps in the problem. Okay, so here's our orthonormal basis coming up. We'd look at the first vector and we'd say its length is √4, or maybe easier just to say 2. So we go 1/2 times 1, 1, 1, 1. Length of the second vector is √10, so we'd go 1/√10 times -2, -1, 1, 2. And then for the third vector there, you can check that the length is √910. So we go 1/√910 times our vector 16, -17, -13, 14. So there we go. That's our orthonormal basis, just as a follow-up to that first problem. So this procedure that we just applied is called Gram-Schmidt orthogonalization. It's the same name whether you're finding an orthogonal basis or whether you're finding an orthonormal basis. That process is still referred to as Gram-Schmidt orthogonalization. Let's find an orthogonal basis for R3 containing the vector 1, 1, 5. Okay, so the trick for this problem, see, in this problem we don't have a set of vectors to start with, so we're going to need to find our starting point. So let's start with any basis for R3 that contains that vector 1, 1, 5. Okay, so let's say we start with 115, 100, 0, 1, 0. So notice that this is not an orthogonal basis right now, but it is a basis for R3. Yeah, let's talk in a little bit more detail about how exactly we know that's a basis for R3, and then we can come back to the calculation. So according to the fundamental theorem of invertible matrices, we've got a statement that says a certain determinant is going to be non-zero if and only if the columns in this matrix here form a basis for R3. So if we were to put these vectors here into the columns 115, 100, and 0, 1, 0, this determinant here is going to be non-zero exactly when these columns, or these vectors that we're interested in, form a basis for R3. So it would be good enough just to calculate this determinant. If you calculated it, you would find that it comes out to a non-zero value, and that's what tells you for sure that the columns form a basis for R3. And let's say that justifies starting with this set here. Okay, so we've now figured out our starting point. Notice that we put 115 in as our first vector, because we know that vector is not going to be changed. So at the end of the problem, we know 115 will be one of our basis vectors in the orthogonal basis, but the second and third vectors will get changed to create vectors that are orthogonal to the previous ones. So here's where we're going to start our process then. So we're going to say V1 is just that first vector, 115. And if you like, you can write down your partial basis. I usually just call that x, consisting of that single vector. So that step there, it's almost automatic, no calculation required. And then we get into calculating V2. So now we're going to take the second basis vector, 100, and we're going to subtract off its projection onto our first basis vector, 100 minus, well, the dot product of these two is 1, and then it's all about what we're projecting onto. So length squared is 27 in the direction 115. Okay, and then we said in our previous problem that you can feel free to scale these vectors, no need to deal with fractions here. So let's instead work with 27v2, which would look like 2700 minus 115. So in other words, 26 minus 1 minus 5. So at this point, we've now found our partial basis after the second step. I'm going to call this x. First basis vector was our 115, and our second one, 26 minus 1 minus 5. So as a double check here, you can just confirm dot product of these guys is 0. So we know we've got an orthogonal set so far. It's not a basis for R3 yet, but it will be once we've got that third vector in there. Okay, so last step then of the calculation. So for V3, we're going to take our third vector from our basis in the problem. So let's scroll back for a second. Our third vector, you can see that right at the top of the screen where we've got this arrow here. Third vector is 0, 1, 0. Okay, so we're going to go 0, 1, 0 minus its projection onto x. And what this is doing is it's saying start with 0, 1, 0 and then subtract off any part of that vector that goes parallel to either of your previous two basis vectors. So that's going to leave us with something that's going perfectly perpendicular to both of the previous two vectors. Okay, so if we want to put some specifics on here, 0, 1, 0 minus the projection onto 115 of 0, 1, 0, and then also minus the projection onto 26 minus 1 minus 5 of our vector 0, 1, 0. So 0, 1, 0 minus, now we're going to do our dot product, which is 1. Length squared of 115 is 27 and it's about the vector that we are projecting onto. Okay, and then we're going to go minus projection onto our second basis vector, so that's going to be -1. You can check on your calculator. If you do length squared of the second basis vector, it's 702, and that's going to be in the direction of that second basis vector. Okay, so now we're going to think about scaling V3. What we need is the lowest common multiple of the denominators here. So if we think about our denominators 27 and 702, if you're really careful here, you could check whether 27 actually divides into 702, because if it does, then 702 would actually be our lowest common multiple. So in fact, it turns out that 702 is divisible by 27, and all we need to do is multiply by 702. Often it works out that way in these problems, but if you had chosen a bigger multiple, like if you had just done 27 times 702, that would also be fine. You're free to scale these vectors however you like. Okay, so multiply by 702, you'd have 702 V3 would give you 702 times 010 minus, you'd have 702 over 27 times 115. And the idea here is that 702 over 27 actually works out to 26. That works out pretty nicely. And then you'd have a +1 times 26 minus 1 minus 5. Okay, and then from there, we're getting our third basis vector coming up. So it works out to 0, 675 minus 135. At this point, you might notice something like, oh, all these components here are divisible by 5. So you could scale that down if you wanted. At this point, I would just stop and say it's easy enough just to write down our answer. So here's our orthogonal basis coming up. So we're looking back to the previous step. Right at the top of the screen here, we've got the partial basis from our previous step. So it was 115, 26 minus 1 minus 5. And then we've now built our third and final basis vector, 0, 675 minus 135. So if you wanted to convince yourself that you've done this correctly, just check the dot products of all three pairs of vectors. They all come out to 0. So that is what confirms that we've got an orthogonal basis. And in this particular problem, remember we were asked for an orthogonal basis containing the vector 115. So by putting that vector into the first position, we've ensured that our final answer has 115 in it. Let's take a look at a definition. Given a matrix A with linearly independent columns, we can write A in the form Q times R, where Q represents an orthogonal matrix. So remember that means a matrix with orthonormal columns. And R represents an upper triangular matrix. So when we write A in this form, A equal QR, this is called the QR factorization of the matrix A. In this problem, we're going to find the matrices Q and R for the given matrix A. It's safe to assume here that the columns of A are linearly independent so that the QR factorization exists. So let's start by finding the matrix Q. The way we're going to do that is we're going to apply the Gram-Schmidt process on the columns and then normalize those vectors. So that will produce a matrix Q with orthonormal columns. In other words, we'll have an orthogonal matrix. So let's run through our Gram-Schmidt process. So we're just looking at the different columns of our matrix A here, and we'll consider those to be our vectors. So our first vector, V1, just grabbing the first column of A, and we just immediately put that into our partial basis, which we'll call X. So no calculations required in that first step. Now we're going to work on building the second basis vector. So we'll take the second column of A, and we will subtract off its projection onto our partial basis. And what that's leaving us with is a vector that is orthogonal to our basis. So let's try the calculation. We'll go 1, 1, 2, 0 minus, so we're going to be projecting 1, 1, 2, 0 onto this basis vector 1, 0, 0, 0. All right, so to do the projection, we're going to do the dot product. I think I'll highlight the two vectors. Doing the dot product is 1, and then everything else is about what we're projecting onto. So length squared of 1, 0, 0, 0 is 1, and then that's in the direction 1, 0, 0, 0. All right, so that looks friendly enough. Our coefficient here is just 1. So doing that subtraction, we get 0, 1, 2, 0 for our second vector. So now we can write a new and improved partial basis, again calling that x. So now our partial basis is 1, 0, 0, 0, plus this new vector that we've just built, 0, 1, 2, 0. And just do a double check here that these are orthogonal. They are, so that tells us that we're on the right track. So now to build the third basis vector, we'll call this B3. We're going to grab the third column of A, and we're going to subtract off its projection onto X. And what that will leave us with is something that is orthogonal to everything in X. So let's run through the details. We'll have 0, 1, 1, 3 minus, now we're going to project 0, 1, 1, 3 onto our first basis vector. So doing the dot product, that's 0. And so effectively nothing else matters here. This is just going to end up being the 0 vector. But if you wanted to write down the details, it would be divided by length squared of the vector that you're projecting onto, and then times the vector that you're projecting onto. Okay, so basically that's 0 vector. We can ignore that. And then moving on to our second basis vector, here it is, the 0, 1, 2, 0. So doing the dot product of this guy with this guy, dot product gives 3. And then everything else is about this vector over here that we're going to be projecting onto. So length squared is 5, and that's in the direction 0, 1, 2, 0. Now remember that we're free to multiply these vectors. We can scale them by anything we like just to avoid fractions. So let's instead work with 5v3. That would be 5 times 0, 1, 1, 3 minus 3 times 0, 1, 2, 0. And that way we can just work with integer components and make life easier. All right, so first component is going to be 0. Second component, 5 minus 3 is 2. Then we've got 5 minus 6 is -1. And then for the last component, 15. So at this point, what we've done is we've built an orthogonal basis. I can now call this B because it's no longer a partial basis. We really are done the orthogonalization process. So we'll just pull our partial basis from the previous step, which was 1, 0, 0, 0, 0, 1, 2, 0, and we've now built our third basis vector, 0, 2, -1, 15. So if you wanted to double check this process, just confirm that all 3 pairs of vectors really are orthogonal. We know the first 2 are because we checked that after the second step, but just check that this new vector that we've just built really is orthogonal to the first 2 basis vectors. It is, so that tells us we've done the process correctly. Now what we're trying to do is create an orthogonal matrix, so we do want to normalize these vectors. So let's write a normalized version of this basis, and then we'll be able to create our matrix Q. So we're just going to go through this basis and divide each vector by its length. Length of the first vector is 1, so it doesn't need to be adjusted. Length of the second vector is √5, so we're going to go 1 over √5 times 0, 1, 2, 0. And then for the third vector, you can check the length. It's √230, so 1 over √230 times 0 to -1, 15. Okay, and that's our normalized basis. So we now have an orthonormal basis for the columns of A. So from there, we're going to write down our matrix Q. So to build our orthogonal matrix Q, we're just going to insert these orthonormal basis vectors into the columns of Q. So first column, 1, 0, 0, 0. For the second column, we need to write things like 0, 1 over root 5. So second column, 0, 1 over root 5, 2 over root 5, 0. And for the third column, 0, 2 over the square root, negative 1 over the square root, and 15 over the square root. So there's our orthogonal matrix Q with orthonormal columns. Now we have to figure out how to get R, because remember the question was asking us to find Q and R for the QR factorization. So to find R, let's think about what we know. We know that we're going to be writing A as Q times R. And we know that Q is an orthogonal matrix. So if we were to multiply both sides on the left by Q transpose, we would have Q transpose A, and we would have Q transpose Q times R. Now remember, with orthogonal matrices, Q transpose times Q is equal to the identity matrix. That's just a property of orthogonal matrices. We're just saying, oh, if you want R, take Q transpose times A. All right, so just one matrix multiplication then to figure out R. So we're going to write down the transpose of Q, and we're going to multiply that by the original matrix A. So let's transpose Q. First row is coming from the first column of Q. So here we have Q transpose just from transposing the matrix Q that we found above. And here we have the original matrix A from the question. So we'll multiply these out in the usual way, and that will give us our matrix R. So what we're going to have is a 3 by 3 matrix. Let's just imagine circling the rows of our first matrix here to do our matrix multiplication. So as we dot our first row with the various columns, we're going to have 1, 1, 0. For our second row dotted with the first column gives us 0. For the second row dotted with the second column, let's think about this for a second. So notice that all the entries in the second row are over root 5. So really when I do this dot product, I'm just going to think about the numerators. I'm going to go 0 times 1 plus 1 times 1 plus 2 times 2 plus 0 times 0. I'm going to say that's 5. So the answer is 5 over root 5. Similarly, doing the second row with the third column here, again, just think about the numerators. So 0 times 0 plus 1 times 1 plus 2 times 1 plus 0 times 3. That gives us 3, so that's 3 over root 5. So that's just sort of the fast way of doing the algebra. So same thing for the third row now, dotting with the various columns. We've got 0, we've got 0, and then third row with the third column, just thinking about the numerators, 0 times 0 plus 2 times 1 minus 1 times 1 plus 15 times 3. So that gives 46. So answer is 46 over root 230. So notice that this is an upper triangular matrix, as it is supposed to be. The whole point of QR factorization is that your matrix Q is orthogonal and your matrix R is upper triangular. So we've completed the problem. We've figured out the matrix Q and the matrix R that multiply together to give us our matrix A. So let's talk briefly about why we care about the QR factorization. So I'm going to show you an application of QR factorization. It's something that you may use in other courses. This will not be tested. So it's something that I show you just sort of out of interest so that you can understand why we cover the QR factorization. So we're going to talk about approximating the eigenvalues of a matrix. Okay, imagine that we have a large matrix, maybe 5 by 5, maybe 8 by 8, something like that. And we want to approximate the eigenvalues of our matrix A. Maybe we just want to figure them out to one decimal place as opposed to finding the exact values of the eigenvalues. So what we would do is find the QR factorization for our matrix A. Okay, so we can do Gram-Schmidt relatively quickly. And then from there we saw it's quite quick to get R once you know your matrix Q. So we would find that QR factorization. And then we would create this new matrix, which we're going to call A1. And what we're going to do is we're just going to take the R and the Q that we found, write them in the opposite order, and multiply them together. So we're going to let A1 be R0, Q0, where Q0 and R0, just the name we gave to the matrices from the QR factorization. So just reversing the order, multiplying them together. Okay, and you get some new matrix, A1. Then what are we going to do? We're going to find the QR factorization for this new matrix, A1. So the Q and the R, we're going to call them Q1, R1. And the reason we need these subscripts here is just because we're going to keep doing this process of finding a QR factorization. Okay, now multiply those matrices together in the other order. That's now just some other matrix. Find the QR factorization for that. So all of those processes are, let's say, relatively quick compared to working out the eigenvalues of the matrix directly. Now here are the facts that are going to be really useful to us. So matrix AK has the exact same eigenvalues as your matrix A. And that's true for all the K values. So running through our list here, if you think about the eigenvalues of A, they'll be exactly the same as the eigenvalues of A1, which are exactly the same as the eigenvalues of A2, etc. If you wonder why that's true, it has to do with the fact that Q is an orthogonal matrix. So this process of finding the QR factorization and then multiplying those matrices together in the other order does not affect the eigenvalues. That's just a property of orthogonal matrices that makes them particularly nice to work with. So let's think of that as important fact 1, and then important fact 2. If the eigenvalues of A are real with distinct absolute values, then the sequence of matrices AK becomes upper triangular, meaning the entries below the diagonal are approaching 0, and they get closer and closer to 0 as you iterate this process. So the more matrices you look at, the closer those lower entries get to being 0. So let's just talk about this clause here where we say eigenvalues of A are real with distinct absolute values. So for example, if your eigenvalues are, let's just do a scenario where we're talking about a 3x3 matrix to keep it simple. So let's say your eigenvalues are -2, 1, and 3. Then all your eigenvalues are real and they all have distinct absolute values. The absolute values are 2, 1, and 3. This would not work for something like lambda equal -2, 1, 2, as the eigenvalue or the absolute values are not distinct, right? So -2 and 2 have the same absolute value. So for this matrix here, the QR factorization process for approximating the eigenvalues would not work well. But if you just sort of think of all the large matrices out there and just make a random choice of matrix, most of the time, your eigenvalues will have distinct absolute values. So this process is pretty useful for the majority of matrices. All right, so what we're saying is that if you take a matrix A that has this nice property with the eigenvalues, then after you iterate this process enough, let's say you've done, I don't know, maybe 5 steps and you've built this matrix A5, what you're going to see below the diagonal are entries that are very close to 0. So you might see entries like 0.1 or -0.05. They're all going to be approximately 0. So we can say this matrix then is approximately upper triangular. And what do we know about upper triangular matrices? Well, we know that the diagonal entries of an upper triangular matrix are the eigenvalues. So we can say the diagonal entries of this matrix AK approximate the eigenvalues of A. So you may see this approximation method in some of your other courses. And this is why the QR factorization is typically covered in linear algebra. So that's our video on Gram-Schmidt orthogonalization. Thanks for watching.